Welcome to Non-Euclidean Geometry lesson number 7. In this lesson we're going to talk about three related topics: equivalence, area, and then circles in hyperbolic geometry. We have the concept of equivalent polygons in this slide. And I'll give you an example here. If you recall, we had this figure from our previous lesson. We started with a triangle A, B, C, and then we generated a secure quadrilateral B, D, H, C. And if you recall further, we had this, I just want to point to it here, this triangle AEF. This triangle was congruent to this triangle DEB. And then this triangle here, AFG, we showed was congruent to GHC. And so what we have is the triangle ABC is consisting of four smaller triangles, AEF, AFG, and then this here BGE and BCG. And those four triangles are congruent to four triangles in our secure quadrilateral. This to this is an overlap, so they share exactly the same. Then this again is an overlap, and then this triangle to that. So the two figures, the triangle ABC and the quadrilateral BDHC, they have a congruent set of triangles that compose them, and in that case they're said to be equivalent. And we have a more general definition here. If two polygons can be partitioned into the same finite number of triangles and a one-to-one correspondence can be established so that pairs of corresponding triangles are congruent, which is what we've done here, the two polygons are said to be equivalent. And we also have a theorem more specific to a triangle and its associated secure quadrilateral. In general, a triangle is equivalent to each of its associated secure quadrilaterals. And we kind of showed that for one case here. We have a few theorems on this slide concerning equivalent polygons. First theorem is if two polygons are each equivalent to a third, then they are equivalent to one another. So this is basically a transitivity property. I'm not going to prove it here, but I'll give you a reference to a book by Wolf. I believe it's available for borrow from the Internet Archive, and I'll give you the reference to that. But it's theorem number 1 in section 62. Then the next theorem holds for hyperbolic geometry, but not for Euclidean geometry. For example, in Euclidean geometry, similar triangles of different areas are clearly not equivalent. We know that. But in hyperbolic geometry, two triangles are equivalent if and only if they have the same angle sum or equivalently the same deficit. You remember we defined the angle deficit in the previous lesson. And that's proven in two theorems from a book by Gans, which I gave you a reference to this earlier, but I'll include it again in the information to this video. It's also possible to derive trigonometric formulas in hyperbolic geometry. You can find those in the Wikipedia article, Hyperbolic Triangle. It's kind of long, and I'm trying to keep this series of lessons more to a summary of things, so I felt this was maybe getting a little bit too much into the details. But if you're interested, there's the formulas are in Wikipedia article, Hyperbolic Triangle, and also in this same book here by Gans in sections 5 to 7. He has a lot of detail on that, and you can see it takes up 3 sections in a book to actually cover all this. We have something called a measurable set in geometry. That just means that we can assign a meaningful value to either a length or an area or a volume or even something in higher dimensions. There's also things called non-measurable sets. We're not going to talk about those here. I'll give you a reference. It's kind of an advanced topic in mathematics, but we're going to stick to measurable sets, which is probably what you would have assumed if I didn't even mention this. But in Euclidean geometry, if we dissect a measurable planar set, so a set that you can measure in the plane, into several measurable planar sets, then the area of the constituent sets adds up to the area of the original set. So for example, if we cut a square into two along one of its diagonals, the sum of the areas of the two resulting triangles equals the area of the square. You would probably have assumed that without even giving it a second thought. However, in hyperbolic geometry, we have some unusual things going on, and we want to make sure that we have that same property, that if we dissect or trisect or whatever, we cut a planar object in hyperbolic geometry into multiple pieces, that the area of the pieces add up to the area of the whole. And there's different approaches that don't work. I won't go into those, but the approach that does work is to use the deficit of a triangle to define area. So if you recall from Theorem 19, the deficit of a triangle ABC, I have a little picture down here, is the deficit of the two component parts, so ABD and ADC, and we just have it written out here. So that works, and that, in fact, that's what's used with a slight variation to define the area of a triangle. I have it here. The area of ABC is equal to some constant times the deficit of ABC. And we can test that out here with our example. The area of ABC, using our definition, equals constant times the deficit of ABC. And then this deficit ABC is the deficit of these two pieces here. And then we have this here, so it would just be C times this deficit and C times the deficit of the second constituent triangle. And then by definition, this is the area of ABD, and this is the area of ADC. So this constant variation on just defining it as the deficit alone, it still works if you put a constant in here. That leads to some unusual things because you need to decide on what to pick for that constant, which we'll get to later on. But for now, we'll just keep in mind that the area of a triangle is defined to be a constant, yet to be determined, times the deficit of the triangle. In general, and then not talking about hyperbolic geometry or areas, if we have a function and it has this property here, f of x plus y equals f of x plus f of y, and f is a continuous function, then the only solution is of the form f of x equals a constant times x. This is known as the Cauchy's functional equation. And I'll give you a link to this if you're interested in more detail. But the important thing is that any function that has this property has this unique solution up to a constant, assuming f is continuous. As is, our problem does not actually fit Cauchy's functional equation. And we're talking about the area now again. So, however, by Theorem 25, we know that the triangles with the same angle sum are equivalent. So we can replace a triangle by its angle sum x in our area formula, and then we have the area of x plus y. So instead of the actual triangle itself, we're just putting in the x to represent the angle sum and y the angle sum of another triangle. And then the area of these two angle sums equals the area of each one individually. So viewed in this way, we can apply the result concerning Cauchy's functional equation, this here, and that gives us that the area of a the angle, using the angle sum of a triangle is just a constant times the area of x. So by our definition of area, two triangles have the same area if and only if they have the same deficit. And by theorem 25, if and only if they have the same angle sum. So we can summarize all this in a theorem here. Two triangles have the same area if and only if they have the same angle sum. So clearly this is different from Euclidean geometry where all triangles have the same angle sum, 180 degrees, but we know that they have different areas. If we take, for example, c equals 1, that's our constant we're talking about, then the largest possible area for a triangle in hyperbolic geometry would be less than 180 degrees, right, because we're assigning it to the angle sum here, or pi radians. That's these two things, depending on how you want to go, these two things are equivalent, which corresponds to an angle sum approaching 0. So areas are quite different here. We'll explore this a little bit more as we continue in the lesson. Given our early analysis of polygons, where we showed that we can always subdivide a polygon into a collection of disjoint triangles, we can now define the area of a polygon as just being the sum of the areas of the triangles that in any given partition of the polygon. We can also define the deficit of a polygon. I have that here. If the difference between n minus 2 times 180 degrees and the sum of the angles of a polygon is defined to be the deficit of a polygon, which is what we're going to do, then it follows that the deficit of a polygon is equal to the sum of the deficits of all the triangles in any partition of the polygon. So that's just fortifying or justifying, I guess maybe is a better word, our definition of area for a polygon. Then we have a few theorems here that I'll just read off. I'm not going to prove these. Some of them are fairly apparent from what we just set up here. Two polygons have the same area if and only if they are equivalent. So in other words, if they have the same side lengths and the same angles, same number of sides, of course. If a polygon is partitioned into triangles in any way, then the area of the polygon is equal to the sum of the areas of all the triangles in the partition. So that's almost the definition. And then if a polygon is equivalent to two or more component polygons, the area of the polygon is equal to the sum of the area of the components. So that's just saying if you divide the polygon into large figures that have more sides than triangles, for example, let's say you could divide a polygon into two squares and a triangle, then the area of the polygon is equal to the sum of the areas of the two squares in the triangle. That just is one example. In hyperbolic geometry, we define a circle the same way as we do in Euclidean geometry. It's the set of all points that are the same distance from some given point, its center, and the distance is known as the radius. We have other terms here that carry over from Euclidean geometry: diameter, arc, chord, and so on. You can look at book 3 of Euclid's Elements. I'll give you another reference to this in the information to this video if you want to look that up, but it's the same terms are used again here. The other thing we have is that all the propositions from book 3 of Euclid's Elements concerning circles that do not depend on the parallel postulate, postulate number 5, also hold true for hyperbolic geometry. And what I'm going to give you are some examples on this slide and going into the next slide concerning these propositions for circles that hold true in hyperbolic geometry. So I'm going to use this diagram here for the next few propositions. So the first one is, given any 2 points on the circle, say here and here, then all the points on the chord, this red thing, connecting the 2 points is inside of the circle. That's pretty obvious, and that holds true for hyperbolic geometry too. Then the second one proposition is that a line passing through the center of the circle and bisecting this chord, any chord, forms right angles with the chord. So these 4 angles here that I'm pointing to are all right angles. And conversely, if you have a line passing through the center of a circle that intersects the chord at a right angle, then it bisects the chord. 2 chords of a circle which are not both diameters cannot bisect each other, although one may bisect the other. So I'm showing here another chord in green, and the green chord bisects the red chord, but the red chord doesn't bisect the green chord. That's this proposition is saying that's always true. You can't have 2 chords that bisect each other unless they're diameters. We have a few more propositions that hold true for circles in hyperbolic geometry. The first one says that if we have 2 circles that are tangent, I have the 2 cases drawn down here, then the points, the center of the 2 circles and the point of tangency must lie on a straight line. So in here the 2 circles are external to each other, and you have the center here, this intersection point of tangency, and then the other center. And this proposition is saying those 3 must be on the same line. And then here you have one circle inside of another. They're tangent. So you have this tangency point, this center, and then center of this bigger circle. And again, all 3 of those points lie on the same line. And that's a proposition that could be proven in both Euclidean and hyperbolic geometry. The second 2 propositions are related. The first one says, at a point of tangency of a line L to a circle, so you have a line tangent to a circle at one point, a radius drawn to the point is perpendicular to the tangent line. Going the other way, if line L is tangent to a circle at a point P, the line M perpendicular to L at point P must pass through the center of the circle. And both of these are used quite often in various proofs. And then we have one more. In the same circle or congruent circles, equal central angles subtend equal chords. So I have here 2 central angles. The first one is between these 2 red radii, and the second one is between the 2 green, and they're both the same angle. And what this is saying is that if that's the case, then the chords that they sweep out, in this case the dotted red and the dotted green, are of the equal length. Now, not everything carries over. There are some properties of circles that hold in Euclidean geometry that are different or don't hold at all in hyperbolic geometry, and I have a few examples of those here. The angle inscribed in a semicircle is a right angle, so that's true in Euclidean geometry. I have a drawing of one example here. So if you have a diameter and then you pick any point on the circle and you connect the 2 vertices, 2 endpoints of the diameter to that point, then this angle in here that I'm pointing to is always 90 degrees in Euclidean geometry. This is not true in hyperbolic geometry. We'll see in the next slide that I'll prove this angle is acute, less than 90 degrees in hyperbolic geometry. An inscribed angle is measured by half its intercepted arc. That's not true in hyperbolic geometry. An angle inscribed in a circle is less than half the central angle subtending the same arc. So I have a drawing here of that. So here's a central angle. The red radii are bounding the central angle here. And in Euclidean geometry, this angle here, where you have the point on the circle, is half. This angle is half this angle here. And what we're saying in hyperbolic geometry is an angle inscribed in a circle, this green, is less than half the associated central angle, this angle in here. Okay, so that's a little bit complicated. Hopefully you got it from the example picture here. Then we have one more. Any three non-collinear points determine a unique circle. So that's very well known in Euclidean geometry, but it doesn't hold in every case for hyperbolic geometry. As I mentioned on the previous slide, the angle inscribed in a semicircle in hyperbolic geometry is acute, and what I didn't say is it also varies depending on its location. So where we have an example down here, we have A and C as the diameter, M is the center of the circle, and we pick some point B here. What we want to show is that the angle ABC is less than 90. And we also want to show that as we move this point B around, the angle varies. So you get a different angle ABC as you move this point. And that's not the case in Euclidean geometry. No matter where you put B, this angle is always 90 degrees. Okay, so I have a few extra things on this figure, which I'm going to talk about on the next slide when I actually do the proof. Let's complete the proof. By theorem 15, the angles at A, B, and C add up to less than 180 in hyperbolic geometry. Then the triangle AMB is isosceles because AM equals BM. The AM and BM are both radii. And so the angle here, ABM, is equal to the angle at A, which I've written here. By a similar argument, BMC is isosceles, and so the angle MBC equals the angle at C. Have that here. And we just add A plus C together, but we take these two equivalents, and we get ABM plus MBC, which is just angle B here. So A plus C equals the measure of B. And we plug that into here, and we get A plus C is B. So we get 2B is less than 180 degrees. And if we divide both sides by 2, we get that B is less than 90, which is what we wanted to prove, that this angle up here is less than 90. It's an acute angle. The second part of the proof is a bit intricate, and I'll go through it slowly here. So let's take a line here, CD, tangent to the circle at C, and we'll keep the points A and C fixed. And what we want to prove is that as we move B, the angle here at B, A, B, C, that angle, it changes. So as B approaches C, so as we move B along here and we approach C, the line AB approaches AC, so this line here becomes closer to this line AC, and the line BC, this one here, approaches the line CD, respectively, the way I've written it here. So further, B, this angle B here, as you get closer and closer, it approaches the angle ACD, which is 90 degrees. So if the angle B had a constant value for all locations of B on the circle here, the value would need to be 90 degrees. But this contradicts the first part of the theorem, that B is less than 90 degrees, what we proved right here. So therefore B, the angle at B must vary, which is what we wanted to show. Okay, so that's the last slide in this lesson. I have quite a few more on hyperbolic geometry, and I will put a number of references in the information to this video.